In this video I will show you how you can record a simple current voltage characteristic of a resistor and also of a light emitting diode, an LED. And the idea here is to show you how this can be done in practice by using a multimeter, and also that you can see the difference between an ohmic resistance, which is the resistor, and a non-ohmic resistance, a non-linear device such as a light emitting diode. My name is Andreas from the Fearless Engineer, and here we go. Now, before we look at the actual experiment, let's briefly discuss the motivation behind this video, why it makes sense to watch this and why it makes sense to know about such things as current voltage characteristics of electronic components. We have seen before in a previous video, if you have watched it, that such a characteristic describes the behavior of a component for different operating points. An operating point is, for example, a specific voltage drop which we imprint upon a certain component. Let's say we connect a resistor to a 9-volt battery, then this connecting to a potential difference of 9 volt will cause a certain current flow through this component, which in this case, if we use a normal resistor, obeys Ohm's law. And in the case of non-linear components, for example a light emitting diode, this behavior will look differently, and it will greatly depend on how this curve is shaped. And in order to tell how a component might behave in a circuit, we can use the characteristic curve and apply the knowledge which we have gleaned from the previous video to design a circuit in an appropriate manner. And in this video we're going to record two current voltage characteristics, one for a resistor and another one for an LED. And in order to do so, we will first set up the circuit and connect the measuring devices we need for this, for voltage drop measurements and for amperage measurements. Then we will record the characteristic for this said resistor, and then thirdly we will record the characteristic for a light emitting diode. But before we dive right into the experiment, let's look at some theory items which you need to understand before. If you, for example, have not watched the video on current voltage characteristics, you can see two such characteristics here, one for a so-called linear component. This might well be a resistor, and the second one, represented by this red curve here, is a non-linear component. This might well be a light emitting diode, and this shows non-ohmic behavior, and the green one shows ohmic behavior. And for the green curve, we can say that for all pairings of voltage and current, the slope of this curve is identical. It's constant. The slope of this curve is given by the resistance value. The slope is the inverse of the resistance value, which we have seen in the previous video. And you can be sure that for every setting of voltage drop you choose, the increase in current flow will be predictable if you only know the resistance value of this device. This is going to be different for the red curve here. The red curve has different behaviors in different intervals of the voltage axis. For example, in this first interval here, the slope is quite shallow, and then we have this nonlinear transitioning phase here, and afterwards in this interval here you have a strong increase in current flow for only a slight change in the voltage drop. This, for example, might be the current through an LED, which increases exponentially once you approach a certain threshold voltage. So a characteristic curve tells you how this component will behave. And you can section it into different intervals, for example the first interval here, the second interval there, and in these intervals you can assume linear behavior, and this linear behavior can be described by a differential resistance which only holds for this interval. And that's enough theory. The rest will become more clear in the actual experiment. So let's go for it. Now let's take a brief look at the setup of the experiment. We have a voltage source which drives everything. Directly in series to the voltage source, connected to the negative terminal in this case, is a resistor, an ohmic component. Then in series to the resistor we have a multimeter which is set to measuring amperage, and directly behind the multimeter comes again the voltage source. And so in the first step we're going to connect this voltage source to the resistor, then we will set different voltages and we will measure the current flow. So we have two readings for each measurement. One is the current flow which we take from the from the voltage source, and the second one is the current measurement which we get from the multimeter. And once we're done of computing all these, of measuring all these pairings between voltage and current, we're going to repeat the same procedure for a light emitting diode, which we enter into the circuit at the position where we formerly measured the resistor. The idea of this experiment is to record the current voltage characteristic of this resistor here. At least that's the first part of the experiment. In the second part, we're also going to do this for a light emitting diode, an LED, but for now it's a resistor. And according to what we heard before, the relationship which this resistor puts between voltage and current should be a linear one, which means that the increase, the slope of the current voltage characteristic should be constant, which should lead to a straight line in the characteristic. And by measuring both current and voltage for this resistor, we will check if this holds true for this device here. On the left we have a multimeter set to voltage measurement, and on the right we have a multimeter set to amperage measurement. And the red cables here are connected to the resistor directly across it, so we measure the voltage drop across the resistor. And the current meter is connected in series to the resistor. This black cable here leads directly into the current meter, and the other one leads out of it. And these two connectors here, this is the output of the amp meter, and this leads back to the power source. And this red connector here, which is connected to the right side of the resistor, leads to the positive terminal of the power source. And what we're going to do now is we're going to run various settings of voltage, and we'll record the measurements of voltage drop across resistor and the current running through the resistor here. Now let's switch on the power source and see what happens when we run this measurement series for this single resistor here. We're going to start with 2 volts, 1.977 and 0.009 amps running through the resistor. Now we increase to 4 volts, 6 volts, 8 volts, we're now at 37 milliamps, 10 volts, 12 volts, 14 volts, 16 volts, up to 75 milliamps, 18 volts and 20 volts. This is where we're going to stop. Now before we look at the numbers in a graph we are going to plot from these measurement series, we will switch the resistor to an LED and perform a similar series of measurements here. Now what you can see here is a light emitting diode in green, and the positive terminal of this light emitting diode is connected to the positive terminal of the power source, and the negative is connected in exactly the same manner as the resistor before to the negative terminal of the power source, and across it we measure the voltage drop. Now as you might recall from the video on voltage current characteristics, this device is not a linear device, which means it has a non-ohmic behavior. The increase of current when we increase the voltage drop does not follow a linear characteristic, which is what we want to find out right now. And to make sure that we get this rapid increase in current flow once we reach a certain threshold voltage, we will increase across a very finely grained series of steps, starting with 1 volts and going up until roughly 5 volts to see what happens to both the current and the brightness of the LED. Now let's start with 1 volts. Now as you can see here on the display, we already have 1 volt laid across the LED, and there's no current flow which we can observe here. Now let's increase the voltage to 1.5. Now we have 1.5 volts, still nothing. Let's go up to 2 volts. Now we have 2 volts, and you can see a faint glow of the LED. Now it's lit up a little bit, and the current flow you can observe is at roughly 8 milliamps, which is not yet that much. And the current across the LED is at 1.983 volts. Now let's further increase the current flow in 0.2 steps. Now 2.2. 2.2. Current flow has increased to 42, 43 milliamps, and the brightness has also increased a lot. It's significantly brighter now. And if we increase the voltage drop even further, now moving to 2.4, you can see that the current flow now is at over 100 milliamps, 128, 29, 30, still increasing a little bit. But the brightness, as you might have observed, did not increase that much. So this operating mode is not very healthy for the LED. It's designed to operate at roughly 25 milliamps, and amperages higher than 25 will significantly shorten its lifetime, and the extra yield in terms of brightness is very, very insignificant. So let's now move on to, let's say, 3 volts, see what happens. Over 300 milliamps, 4 volts. Now the LED has turned off. It starts to smell very badly, and we are already at almost 1 amp of current flowing through the LED. Now it's starting to turn black even. Let's increase a little bit further. 6 volts. And now it has stopped working completely. The voltage is still at 6 volts. However, the current has dropped to 0, which means we have just destroyed the LED. It's made for 25 milliamps. We have had a current of about 1 amp running through it. Now let's take a look at the current voltage characteristic of both the resistor and the LED to see what we can learn from these measurements. Now let's look at the resulting current voltage characteristic of the resistor. As we have anticipated, it obeys a linear characteristic. It's a straight line emanating from the origin, and with every increase of voltage we can exactly predict. There are some slight deviations due to measurement inaccuracies, but the overall picture is clear. For every increase in voltage you can exactly predict by only knowing the resistance of this resistor here what the resulting current is going to be. And also, the steeper the characteristic curve, as we have discussed before, the smaller is going to be its resistance value. And if you only had this curve here, you could perfectly well compute the resistance of the component. Now for the light-emitting diode, the characteristic looks very much different because it has this non-linear behavior. In the first phase, before we meet the so-called threshold voltage, the current flow through the light-emitting diode is almost 0. And up until about 2 volts, a little bit less, the current flow starts to increase. And as you can see, slight increases in current flow afterwards, once we exceed the 2 volt threshold, lead to a very strong non-linear to an exponential even increase in current flow. And once we are at roughly 2.4 volts, something like this, we already have a current flow of almost half an amp. It's 370, 380 amps, which we can observe. And if we increase only a little bit further, as you have seen in the video, we are very quickly at 1 amp of current, and this is the point where this light-emitting diode broke and refused to conduct any current at all. Which is why in practice, but this is a topic for another video, we need to protect such devices which show such a behavior. We need to protect light-emitting diodes with a resistor which prevents this strong exponential increase of current from happening due to its very predictable linear behavior which we have observed in the first phase of the experiment. That's all for now. If you have any questions related to this video, don't hesitate to drop me a comment down below in the comment section. Also, if you have any suggestions for future videos which you want me to make, please also leave a comment here. I wish you a nice day now, all the best, and see you next time here on The Fearless Engineer.